Chapter 9 is about chemical equilibrium and reaction rates. In this chapter, we'll discuss rate of reactions, chemical equilibrium, using the equilibrium constants, and we will finish it with Le Chatelier's principle. What is the reaction rate? The reaction rate is determined by measuring the amount of reactants used up or product formed in a period of time. We can measure the rate of the reaction by the change in concentration of either the products of the reaction or the reactants over time. The rate of a reaction is going to be affected by changing the temperature, changing concentrations, and the presence of a catalyst. By increasing the temperatures, what we're doing is increasing the kinetic energy of the molecules, making them move faster. If they move faster, there will be more collisions, and then the reaction will proceed faster. An example of this is why we put our perishable food in the fridge. We do it to slow down the reaction that will cause it to get damaged. Another thing that we can do to increase the rate of a reaction is changing concentrations. If we increase the concentration of the reactants, the reaction will go faster. And the last thing we can do is add a catalyst. If we add a catalyst, the reaction will go faster. They are designed just to increase the rate of the reaction. So let's indicate if the reaction will increase, the rate of the reaction will increase or decrease by doing this. If we raise the temperature, the rate of the reaction will increase. If we remove oxygen, which is a reactant, it will decrease. If we add a catalyst, the rate of the reaction will increase. And if we make it cooler, then the reaction will slow down. Its rate will decrease. A reversible reaction is one that proceeds in both directions, forward and backwards. We use this type of arrow to show it proceeds in the forward or the reverse. Chemical equilibrium is created when we have the forward reaction and the reverse reaction happening at the same rate. If that happens, the concentration of the products and the concentration of the reactants do not change. They remain constant as long as they are in equilibrium. So if we have a reaction like this, we see that this is a forward reaction. The reverse reaction will be in this direction. So we can write the reaction using this type of arrow. Means that this reaction is in equilibrium. So let's write the forward and the reverse reaction for this equilibrium reaction. So the forward will be this. And the reverse will be this. Alright, so let's answer this question. We are going to use either equal, not equal, forward or reverse, changes or does not change to complete each one of these sentences. Reactants from products is the forward reaction. At equilibrium, the reactant concentration does not change. It remains constant. When products form reactants, it is the reverse reaction. Number 4 says, at equilibrium, the rate of the forward reaction is equal to the rate of the reverse reaction. And number 5 is not shown here, but it's in your PowerPoint presentation, and it says, if the forward reaction is faster than the reverse, the amount of product changes. So when we have an equilibrium, we will express what is called the equilibrium constant, or Kc. For the equilibrium constant, what we use is the concentration of the products divided by the concentration of the reactants. It's important that we look at the balanced stoichiometric coefficients of the equation. They will be important when we are writing the equilibrium constant. So, the first thing we need to do is write the balanced chemical equation, put the concentration of the products in the top of the fraction, the concentration of the reactants in the bottom, and look at the coefficients. Let's do a problem. So the equilibrium constant here is going to be, these are the products. So we got concentration of the products raised to the power of the stoichiometric coefficient divided by, so we look at oxygen, its coefficient is 1, so we don't have to write anything, and CO is A2, so we need to square this one. So let's see which one of these matches for the Kc of this reaction. So we have, in the top, we need to have NCl3 raised to the power of 2. This is not an option, this is not an option, this is good, this is good. Now, we need to have at the bottom N2 raised to the power of 1 and chlorine raised to the power of 3. So this is not an option. The only answer possible is D.